Resistance is the opposition to blood flow due to friction between blood and the walls of blood vessels. By blood, I don't just mean red blood cells and white blood cells. I also mean blood plasma. So this is friction between not just the solid but the liquid components of blood. Vascular resistance depends on three factors: total blood length, the size of the blood vessel lumen, and blood viscosity. So we're going to examine each of those at a time. Systemic vascular resistance can also be called total peripheral resistance, and this is essentially all of the vascular resistances due to all of the systemic blood vessels. So basically this is generated by friction between all of the blood in the circulatory system and the walls of all of the blood vessels in the circulatory system as well. The biggest contributor to total peripheral resistance is by arterioles, capillaries, and venules, and the reason why is because they're the smallest and also because they're the most numerous. We'll see how their size affects resistance in just a moment. So the velocity of blood flow is inversely related to the cross-sectional area, in other words, the area of the lumen. And what's meant by that is basically the greater the cross-sectional area, the more lumen that there is, the slower that blood flows. So when we're talking about total cross-sectional area, we're talking about the area of all of the branches from your original blood vessel. So basically, as an artery branches from one vessel to two vessels, the cross-sectional area is greater for the two branches, and in the region of this branching, the velocity is slower. So what I'd like for you to do is to take a moment, pause the video, count the number of squares in the larger blood vessel at the top versus the number of total squares of the two blood vessels at the bottom. It wouldn't be unreasonable to think that you could have a branching with arteries with something like the two sizes I've got here. So think of where the abdominal aorta branches out into the two iliac arteries. So you would see two branches that were proportionally about the same size as the bottom two are to the top two. So if you count all the squares in the top blood vessel, including partial squares, and add those all together, I usually get around between 26 to 28 estimated by students. And with the bottom two blood vessels, when you count those two together, generally my classes estimate between 32 and 34 squares total between those two. So if you take a look at the figure at the bottom, you'll see that you start with the aorta and you proceed to the arteries, arterioles, capillaries, venules, veins, and then the superior and inferior vena cava. And basically what the blue line represents on this particular figure is the total cross-sectional area. Now, you begin with the aorta, which has a diameter of about 3 to 5 square centimeters, which is a little over 1 inch to 2 inches squared. Your velocity is about 40 centimeters per second, which is about 16 inches per second, so pretty fast. However, you have so many branches that lead out to the capillaries, and so many capillaries themselves that even though on an individual basis they're microscopic, their diameter is 4,500 square centimeters. And that means with the diameter moving from 3 to 5 centimeters squared to 4,500, a factor of almost 100, your velocity is going to drop from 40 centimeters per second to 0.1 centimeters per second. Now, this slowdown in velocity, as we'll see a little later on this chapter, is not a bug, it's a feature. The reason why velocity being slow in the capillaries is a good thing is because this gives nutrients and oxygen time to diffuse out of the blood while the blood is still in the capillaries. Likewise, CO2 and waste products have time to diffuse into the bloodstream from the cells that the capillaries are contacting. So this is another graph that shows you the total area in square centimeters of the circulatory system and how the velocity of blood drops as you get to the capillaries. So again, once you get to the capillaries, both the velocity and the rate of blood flow have dropped to really low levels, and because the velocity and the rate of blood flow have dropped, this is going to allow time for, again, materials to diffuse both out and into the bloodstream.